Okay, this is your instructor again, Tom Perepsky, and we're in Module 7, and this is the third part of the module. We're going to talk about the sampling distribution of p-bar and point estimation. It's time to introduce a new parameter and a new statistic. We're going to let p equal the population proportion, and p-bar is the sample proportion. As with any statistic, p-bar has a sampling distribution to it. So the sampling distribution of p-bar is the probability distribution of all possible values of the sample proportion. You might be able to see that the distribution of p-bar is closely related to the binomial distribution that we talked about earlier. Remember, a binomial variable x counts the number of successes in n trials. You could get 0 successes, 1, 2, on up to n. The sample proportion of successes would be x divided by n, or what we're calling p-bar. For example, if I flipped a coin 100 times, the number of heads could be 0, 1, 2, 3, on up to 100, and that would be the binomial variable. The sample proportion of heads could be 0 out of 100, 1 out of 100, 2 out of 100, all the way up to 100 out of 100. So p-bar can be thought of as just x divided by n. As always, we need to know three things about a sampling distribution. We want to know something about its mean, its standard deviation, and its shape. It turns out that the expected value, or the mean, of p-bar is exactly the same as the population proportion p. This might seem a little bit familiar to you from going over the distribution of x-bar, the sample mean. Remember there we argued that if you averaged all the sample means, you get the same value as the population mean. Well, this is fairly similar. It basically says if you averaged all the sample proportions, you get the population proportion. The standard deviation, sigma p-bar, which by the way is called the standard error of the proportion, is going to be the square root of p times 1 minus p over n. Again, you don't have to worry about the algebra or where these formulas come from, but this is what we will use for the mean and standard deviation of the sampling distribution of p-bar. Finally, and this also shouldn't be too surprising, we're going to argue that the distribution of p-bar is approximately normal provided n times p and n times 1 minus p are at least equal to the number 5. You might recall that was the same criterion we had when we did the normal approximation to the binomial distribution. We argued earlier that a binomial distribution could be approximated by a normal curve, provided n times p and n times 1 minus p exceed the number 5. Well, since the sampling distribution of p-bar is closely related to the binomial, it's really just sort of a transformation of it, it shouldn't be that surprising that the distribution of p-bar will also be normal, just like the binomial was, with the same criterion. And now we're going to do the same thing that we did with x-bar. We now have a new normal variable, p-bar. We know that its mean is equal to p, its standard deviation is sigma p-bar. Therefore, we could answer probability questions about p-bar by converting it to z. And so we have a new variation on the z formula. Z is equal to p-bar minus p over sigma p-bar. Let's do a couple problems. According to a recent news report, 70% of Americans favor stricter gun laws. Assume that 0.7 is the population proportion of Americans that favor stricter gun laws, and we take a random sample of 100 Americans. First, again, I ask you to describe the sampling distribution of the sample proportion, and then I ask you, in the sample of 100 Americans, what is the probability of getting a sample proportion that's within 0.05 of the population proportion? Remember again, whenever a question asks you to describe or explain the sampling distribution, you want to know three things. You want to know the mean, the standard deviation, and the shape. So, since we were given in the problem that p is 0.7, that 70% of Americans favor stricter gun laws, n is 100, first we know what the mean of p-bar is. The expected value of p-bar is exactly the same as p, so that's 0.7. We can calculate sigma p-bar by taking 0.7 times 0.3 over 100 and take the square root of the entire term, and you will get 0.0458 as the standard error of the proportion. Lastly, over here, we should check the normality condition, although this is rarely ever not satisfied. N times P would be 100 times 0.7, which is 70. N times 1 minus P would be 100 times 0.3, or 30. Both of them exceed the number 5, so we can assume a normal distribution. Now, the second part of the problem asked you to find the probability that the sample proportion is within 0.05 of the population proportion. Well, since the population proportion is 0.7, within 0.05 of that would be from 0.65 to 0.75. So in part B, we're basically asking you to find the probability that 0.65 is less than or equal to p bar is less than or equal to 0.75. As always, since it's a normal distribution, we find the probabilities by converting into z-values and either using our table to look up the answer, or those of you with a TI 83 or 84 can use your calculator to find the probability. Converting those to z-values, you take 0.65 minus the mean of 0.7 over the standard deviation of 0.0458. Do the same thing for 0.75. You will get z-values of plus or minus 1.09. Go get the cumulative probability less than 1.09 and subtract off the cumulative below negative 1.09, and you will come up with an answer of 0.7242. So there's about a 72% chance that your sample proportion will be within 0.05 of the true population proportion. And here we can look at this graphically. Here's our distribution of p bar with its mean of 0.7, standard deviation of 0.0458. We convert those values 0.65 and 0.75 to their corresponding z-values and go look up the probability. Let's do a second example, very similar to the first. Assume that 0.8 is the population proportion of Americans who use a credit card when making appliance purchases. Again, we take a sample of 100 appliance purchases. Describe the sampling distribution of the sample proportion, and what's the probability that the sample proportion of those using a credit card will be between 0.7 and 0.9. Again, to describe the sampling distribution of the proportion, we simply need its mean, standard deviation, and shape. With p equal 0.8 and n equal 100, the mean is just equal to 0.8. Recall that the expected value of p bar is the same as the population proportion, so that's 0.8. Plug the numbers in for the standard error. 0.8 times 0.2 over 100, take the square root of the entire term, and you will get 0.04. NP 100 times 0.8 is 80. N times 1 minus P 100 times 0.2 is 20. They both exceed the number 5, so we can assume a normal distribution. Secondly, part B, we want to find the probability that P bar is from 0.7 to 0.9. Once again, we convert those to z-values by subtracting the mean and dividing by the standard deviation. You will get z-values of plus or minus 2.5 when you do that. Look up the cumulative probability below 2.5 and subtract the cumulative probability below negative 2.5, and the answer is 0.9876. Almost a 99% chance that your sample proportion will be between 0.7 and 0.9, assuming the population proportion is 0.8, as you were given. Again, looking at it graphically, here's the distribution of p bar with its mean and standard deviation. We want the probability from 0.7 to 0.9. Those get converted to z-values of plus or minus 2.5, and we go look up the probability. Once again, the reason why we are interested in the distribution of p bar is, of course, what we're going to do in the next module is start talking about estimating things. For example, in these problems, we assumed that we knew that the true population proportion was 0.8, the mean of this distribution. In the future, we're going to say, what if we don't know that? How could we estimate it? Well, logically, you're going to go out and you're going to take a sample, and one of the things you're going to calculate is a sample proportion. You're going to use that as an estimator of your population proportion. Well, then there's a question, how good of an estimator is it? How close to the true population proportion will it come? Well, knowing that this distribution is normal will help us a lot in answering questions like that. Okay, we have one last topic that we're going to take up in this module. I'm going to talk a little bit about the idea of point estimation. A point estimate is a single value that you're going to use as an estimate of a population parameter. For example, if I use the mean of my sample as an estimate of the population mean, that would be an example of a point estimate, a point estimator. We tend to use what I call the logical point estimators in this course. Let's go back to an earlier slide. Remember at the beginning of the module, we talked a little bit about population means, population proportions, and variances. And every time we've had a population parameter like that, we've had a corresponding sample statistic. Well, these sample statistics are basically going to become our point estimators. We will use x bar as a point estimator of mu. We will use p bar as a point estimator of p. S squared becomes a point estimator of sigma squared, and so on. Now, there's some properties of point estimators that I want to talk about briefly. Now, these are mathematical properties, and we're not going to be interested in proving anything about the mathematics of it. But there are some things we'd like a good point estimator to have. The first property is what we'll call unbiased. All that unbiased says is that an estimator is unbiased if its expected value equals the parameter you're estimating. We actually saw in this module two unbiased estimators. Remember when we talked about the distribution of x bar, one of the first things we claimed is that the expected value of x bar is exactly the same as the population mean. That's basically saying that x bar is an unbiased estimator of mu. The same thing was true with the distribution of the sample proportion that we just finished. We started off by saying E of p bar is equal to p. Well, again, that's saying that p bar is an unbiased estimator of p. Now, there's sort of a problem with unbiasedness. It's a fine property, but there can be lots of unbiased estimators. In other words, for example, x bar is not the only unbiased estimator of mu. We could create other estimators. So then you could ask the question, well, which one would we prefer? Well, that gets us to a second criterion here, which we call efficiency. Among the unbiased estimators, the most efficient estimator is the one with the smallest variance in its sampling distribution. Drawing kind of a graph to show the idea here. Suppose we let theta, this is the Greek letter theta, represent any population parameter. And I've got two different estimators, and here are their sampling distributions. Here's the sampling distribution of estimator 2, and here's the sampling distribution of estimator 1. And I've drawn both of them so that you can see they're both unbiased. Their expected values, their mean, equals theta. Which one would we prefer, however? Well, if you look at it, we'd prefer estimator 1. It tends to have a smaller variability around theta. What that smaller variability means is that it's likely to come closer to the thing we're trying to estimate. So we would say that estimator 1 is more efficient. Now again, you just need to know the definitions of unbiased and efficient. You don't need to worry about the mathematics of proving is something unbiased or efficient. Now, point estimators are nice. They give a single value, but the chance of a single value being actually correct is basically zero. For example, if a pollster goes out before an election and takes a sample of voters and finds that 54% of them favor candidate A, let's say, do they expect that come election day it's going to be exactly 54%? Probably not. As I said, that would be sort of a miraculous stroke of luck. You can gain more accuracy by, instead of giving one value as an estimate, you can give a range of values. For example, if instead of saying, I estimate that 54% of the people will vote for this candidate, I could give some kind of a range with some margin of error to it. I could say I estimate that between 52 and 56% of the population will vote for this candidate. Now, those are going to be called interval estimators, and they are going to be the subject of the next module.